Hi, Annalisa. Hi, everybody else. Let's talk a little bit more about that final exam, what kind of things you can expect before Christmas. And here we're talking about a couple of congruent triangles, this ought to say. And triangle ABC is congruent to triangle MNO. I'll tell you lots of things about triangle ABC. I'll tell you about all three sides in terms of these statements. And we know that in triangle MNO, we only know about NO. I'm looking for corresponding parts, and it's clear to me that NO corresponds to BC. So I know that the length from B to C must be the same as the length from N to O. And that gives me this equation. 3x plus 1 must be the same as 5x minus 7. Let's solve that little equation. I'd subtract 3x to both sides. I got 2x here. If I added 7 to both sides, I'd have 8 over there. Divide both sides by 2, and I got x equal to 4. I better figure out about all these sides. Let me find out about BC first. If x is really 4, 5 times 4 is 20 minus 7 be 13. Now this length ought to be the same, NO, and 3 times 4 is 12 plus 1 is also 13. So yeah, that's fitting. What about AB? If x is truly 4, AB would have been 8. And AC is known to be 15. It has to be for the perimeter triangle MNO, but I think I'm going to find the perimeter triangle ABC first. The perimeter triangle ABC is just 8 plus 13 plus 15. That's going to give you 23 and 13 more. There's 36, huh? And if the perimeter triangle ABC is 36, 28, 8, yep, then the perimeter of triangle MNO would be the same. Because they're congruent. They're identical in every way. They'd surely have the same perimeter. The angles of a triangle are in a ratio of 5 to 3 to 1. Give the measures of those angles. You've had some practice with this. What I would like you to remember is if things are in a ratio of 5 to 3 to 1, we could call them 5x, 3x, and 1x. And for all the values of x, these things would be in the ratio of 5 to 3 to 1. But these, because they're the angles of a triangle, we know they add up to 180. And we'll collect like terms, solve this little equation. In fact, I have 9x equals 180. I divide both sides by 2. I'm convinced that x is equal to 20. These were the angles. One of them would be 5 times x. 5 times 20, 100 degrees. One would be 3 times 20. There would be 60 degrees. And then just 1 times 20, just 20. These could be the angles of a triangle, an obtuse triangle. And they're in a ratio of 5 to 3 to 1. Use this figure at right. If the triangle is isosceles with base AC, we do this with a pencil. And DB is an angle bisector. What postulate makes the triangles be congruent? I can do that with this. If the triangle is isosceles with base AC, I should know that these segments are congruent by the definition of isosceles. And if DB is an angle bisector, then I'm certain that these angles would be congruent. Because it must have been the bisector of angle ADB. And then they're saying, well, what postulate would make these triangles be congruent? And I've not yet met a postulate, but if I reflect on a couple of options here, if DB is congruent to itself by the reflexive property, then I could say, hey, I got these triangles to be congruent by side, matching side, angle, side, and that would be perfectly valid. However, you might be thinking, if these two sides are congruent, by the isosceles triangle theorem, that's going to force angle A to be congruent to angle C, and then you can call it angle, side, angle, match an angle, side, angle. I have to accept that also. And then it goes further and it asks me, then why would AB be congruent to BC? If we got these triangles to be congruent some kind of way, why would it be think that this length AB would be as big as that length BC? Yeah, I know what you're thinking. Corresponding parts of congruent triangles are congruent. So once I know the triangles are congruent by one postulate or another, then I can say that the corresponding parts would be congruent as well. Let's look at this. Since we got an isosceles triangle with base AB, I'm going to make a little sketch of such a thing. And let AB be the base of this isosceles triangle ABC. And AC is 12, I'm told. And CB, this length is x plus 5. And I'm getting an opinion about x already. and AB is 2x, and they ask me to find the perimeter of the triangle. By virtue of having a sketch, I know that which two things are congruent. If AB were the base, then these are the legs of that isosceles triangle, so x plus 5 is equal to 12. That makes me think that x is equal to 7. I'm going to find all the lengths I could. Side BC, if x is truly 7, would also be 12. Hey, that's fitting because these had to be both 12. And the base, AB, is 2 times 7, therefore AB is 14. So what's the perimeter of that triangle? And now we got a couple of 12s. That's 24 plus 14. That's going to be 38, huh? For the area of that for the perimeter of that triangle. How many diagonals can be drawn from a single vertex of these polygons? Let me get a good look at that. I'm asked, how many diagonals can be drawn from a single vertex of these polygons? I'm going to look at a hexagon and an octagon. Then I think I'll be able to generalize to the decagon or the 18gon. So, in this polygon, the hexagon, n is equal to 6. You know, that means it has 6 angles and it has 6 sides. If I just chose a vertex, any vertex, I choose this vertex right there. I'm thinking, how many diagonals can I draw from that vertex? And from this vertex, I cannot go from this one to itself, nor can I go to an adjacent vertex. That wouldn't be a diagonal, that's a side. I have to go to a non-adjacent vertex. There's a diagonal, here's a diagonal, and there's the only other diagonal I can draw from that vertex. So I can draw three diagonals. Let's say DSV. For diagonals from a single vertex, I can only draw 3. Now, with this octagon, n is equal to 8 sides and n 8 angles. And if I chose, let me go around here, call this guy ABCD, so we can talk about it. ABCDEFG H. How many diagonals can I draw from vertex A? I can't go from A to A. I can't go from A to B, nor from A to H, but I can go everywhere else. A diagonal from A to C, a diagonal from A to D, a diagonal from A to E, A to F, and from G to A to G. So when n is equal to 8, n minus 3 gives me the number of diagonals from a single vertex, and that would give me 5 diagonals from a single vertex in this figure. 2, 3, 4, 5. And we might wonder how many diagonals you could draw all together, but for right now, let's just go answer these questions. So I'm thinking, well, when n was equal to 6, diagonals from a single vertex was 3. If n is equal to 8, the diagonals from a single vertex was 5. If I've got n equal to 10, the diagonals from a single vertex would be 7. And with an 18gon, how many diagonals can you draw from a single vertex? It would be 15. You gotta leave 3 out every time to get how many diagonals from a single vertex. Then how many diagonals can be drawn in total for those polygons? Now let me go back to this guy. I can draw 3 diagonals from this vertex, and I can draw 3 diagonals from this vertex also. Makes you think you can draw 3 diagonals from every vertex. But honestly, by the time I get to this vertex, one of its diagonals is already shown. I can only just show 2 more. By the time I get to this diagonal, this vertex, 2 of its diagonals are already shown. And when I get to this guy, 3 of its diagonals are already shown. I can't show any more. But there is a formula for this. How many diagonals can you get from a single vertex? N minus 3. How many vertices have you got? N. Don't count anything twice. And there's the formula for the total number of diagonals. 3 from every vertex. I got 6 vertices. I don't want to count anything twice. So that's 18 divided by 2. I should have 9 diagonals in that figure. You can count them if you want to, but I'm sure there will be 9. Let somebody see how many diagonals I can draw in this octagon. I can draw 5 from a single vertex. I guess I could draw 5 from vertex B as well. And 5 from vertex C, and 5 from vertex, 5 from every vertex, couldn't I? However, somewhere along the line, I'm going to start counting everything twice. So, how many diagonals, when n is equal to 8, how many diagonals from a single vertex? 5. When if I can do 5 diagonals from every vertex and I have 8 vertices, it makes you think I can have 40 diagonals. But I would count HB is a diagonal and BH is a diagonal later, so I'm counting everything twice. So it's really 8 times 5, there's 40, divided by 2 would be 20 diagonals all told. So I'm telling you that this is the good formula for how many total diagonals. How many diagonals from a single vertex times how many vertices do you have? Don't count anything twice. So we can figure out these pretty quick and pretty easy. With n equal to 6, I can do 3 diagonals from every vertex. I have 6 vertices. I don't want to count anything twice. So there's 18 divided by 2. I could get 9 total diagonals. If n were equal to 8, 5 diagonals from a single vertex. I have 8 vertices from which to do that. I don't want to count anything twice. So there's 40 divided by 2. I can only get 20. With a decagon with n equal to 10, how many diagonals from a single vertex? I can get 7. 7 from every vertex, and there are 10 vertices. Don't count anything twice. So that looks like 70 divided by 2 has got to be 35. And how many diagonals can you draw on an 18-sided figure? 15 from every vertex, 18 vertices. Don't count anything twice. So that would just be 9 divided times 15, and 9 times 15 is 135 diagonals in that figure. I'll take it just like that. Give the sum of the interior angles in a dodecagon, and you'd have to remember, well, that n is equal to 12 in a dodecagon. And there's lots of reasons to appreciate that question. But there is a formula for the sum of the interior angles, and we'll just hit that formula right here. N minus 2 times 180. That's the formula for the sum of the interior angles of an n-sided polygon. So in a dodecagon, that'd be 12. I got n equal to 12. I should have 12 minus 2 times 180, which should be 10 times 180, which should be 1800 degrees. That's the sum of the interior angles in a dodecagon. What about an octagon? Same formula. So octagon having 8 sides, 8 minus 2 times 180. And that's really 6 times 180. And 6 times 180, 600 and 480 more. That's going to be 1,080 degrees. That's the sum of the interior angles in an octagon. Now this is a pretty good question right here, this irregular hexagon. So as I begin this, it's going to tell me a lot about it, but I know that n is equal to 6 because it's a hexagon. Because it's irregular, I can't predict each angle unless I study what it tells me. There are 4 angles that are 110 degrees each. What do all the angles of a hexagon add up to? I'll go back to that formula. And that would be 6 minus 2 times 180, which is 4 times 180, which is 720 degrees. That's all the angles in this polygon. But I have 4 angles that add up to 110, that are 110 each. So 4 of those at 110 each would be 440. Let me take out that 440 minus 440 there. And that would leave me with 280 degrees, I think. Yeah, that would add up correctly. So I got 280 degrees for all the other angles. Now there are only 6 angles in this hexagon, and I've talked about 4 already, so only 2 angles left, and they're adding up to 240. How big would they have to be each? Give the measure of those 3 congruent angles. That should be 2, shouldn't it? Give the measure of those 2 congruent angles. Now, if they add up to 280, they're going to have to be 140 each. Give the measure of the interior angles in these regular polygons. There's a formula for each interior angle. N minus 2 times 180 divided by how many angles you got, and that would give you each interior angle. And if I had a pentagon, 5 minus 2 times 180 divided by 5. 5 minus 2, that's 3 times 180, would be 540 divided by 5, and that'd be 108 degrees each. 108 degrees for every angle in a regular pentagon. If I had a regular octagon, I'm going back to this formula again. For the moment, and if n is equal to 8, that'd be 8 minus 2 times 180 divided by 8. 6 times 180 is 1,080 divided by 8. I'm pretty sure that's 135. 135 degrees each for a regular octagon. And a regular decagon, let's take a look there. Going to use that same formula, so it'll be 10 minus 2 times 180 divided by 10. So 8 times 180 divided by 10. I could do this division right away and do 8 times 18. And 8 times 18 is 80 and 64, be 144 degrees each. Yep. I think if I had a regular decagon, the interior angles would be 144 degrees each. But let me show you about this last question. If I would have worked this one first, I would have known these answers even quicker. Give the measure of each exterior angle in the polygons above. And what you know is the total, the sum of all the exterior angles, sum of all exterior angles is always 360 for every polygon. So what if I had a pentagon? It has 5 exterior angles, and you say, well, 360 divided by 5 would force each exterior angle to be 72. And the interior angles are the supplement of the exterior angles. That's got to be true. Just take a quick look at this. If I had a pentagon, let me get one real quick. I got a pentagon right here. And if I thought about an exterior angle, clearly it's the supplement of the interior angles. So once I figured out that guy was 72 right there, wouldn't this guy have to be 108? Yeah, that makes sense to me. Let's do this next thing too. The regular octagon, well, what do the exterior angles add up to? 360. How many exterior angles would you have on an octagon? I have 8 of them. So 360 divided by 8 is 45 degrees, excuse me. And that 45 degree angle is the supplement of 135. Yeah, the exterior angles and the interior angles got to be supplementary. One more time with feeling. Give the measure of each exterior angle in these polygons above. Well, if it's a decagon, it's got 10 sides. And if the exterior angles add up to 360, and I know there are 10 of them, they'd be 36 degrees each. And it's nice to know that the exterior angles and the interior angles got to be supplementary. That makes sense to me. That's really the kind of things you got to know in your final exam. Put those ideas together and make a nice page that you can bring to class and whip that final exam and have a nice